Welcome back to Mining of Massive Datasets. We are looking at k-means algorithms for clustering. And we've sort of seen that the k-means algorithm is, produces good clusters, and it's linear for each scan or each round of the k-means clustering, but it can take a really large number of rounds to converge the k-means clustering algorithm. So our question is, can we come up with an algorithm that can do something like k-means clustering, but in one pass over the data if you have a really, really large data set that doesn't fit in memory? The answer to that question is the Bradley-Fayad-Reina or BFR algorithm, which we're going to cover in this segment. BFR is a variant of k-means, and it's sort of optimized for really large data sets that are actually disk resident. The data set is so large that it doesn't fit in memory. And so you really want to just scan the data set once in disk and come up with the clustering. However, to accomplish this, the BFR algorithm makes a very strong assumption. It assumes not only that we have a Euclidean space, which is an assumption that all k-means algorithms make, but it also assumes that each cluster is normally distributed around a centroid in Euclidean space. Let's see what this means. Let's start with a refresher on the normal distribution. Here's a variable x, and here is its frequency distribution, assuming that x is normally distributed. Let's say x has mean 0 and standard deviation sigma. Then if you look at the frequency distribution, it's apparent that we sort of end up with this bell-shaped curve, and most observations of x are going to cluster very closely around the mean 0. In fact, about 68% of the values, which is here 0.34 plus 0.34, so that 68% of observations are going to lie within one standard deviation of the mean, plus or minus 1 sigma from the mean, right? And about 95% of the values are going to lie at a distance of at most 2 sigma from the mean, plus or minus 2 sigma from the mean. And about 99% of observations are going to be at a distance of about 3 sigma from the mean. Right? So this is just a refresher. It should be evident to, most of you should recall this from your elementary statistics classes. Now, the nice thing is, if we assume that that the data is normally distributed in each dimension. Let's say x here is a dimension, and the mean of x is 0, which means that the centroid in x dimension for a given cluster is at 0. Then we sort of know that about 68% of the points lie within one standard deviation of the centroid along the x dimension. And we can say the same thing about each dimension, and we assume that all the dimensions are independent of each other. So in general, we can quantify the likelihood, given that a point belongs to a cluster, we can quantify the likelihood of finding that point at a certain distance from the centroid of the cluster. And this is the property that we're going to use in the BFR algorithm, as it will become apparent later on. Now recall that although in this case, I've shown a single standard deviation sigma, we don't make the assumption that the standard deviation is actually the same along every dimension. Each dimension actually has its own mean and its own standard deviation. Now the implication of this idea that each dimension has its own mean and its own standard deviation is that the clusters actually look like ellipses that are aligned along the axis. For example, here's a cluster, the pink cluster, and notice that it's sort of a flat ellipse that's aligned along the x-axis, which means that the standard deviation is higher along the x-axis than along the y-axis for this particular cluster. Whereas the green cluster here is more elongated along the y dimension, which means that its standard deviation along the y dimension is more than its standard deviation along the x dimension. Whereas the blue cluster looks more like a circle, which means that it has roughly the same standard deviation along both dimensions. So let's start with an overview of the BFR algorithm. Remember that the data set that we're looking at is really, really large, and it's actually on disk. Now the data is so large that it doesn't actually fit, all of it doesn't really fit into memory, right? So what we're going to do is that we're going to page the data, one chunk of the data in at a time into memory, right? When we bring a chunk of data in and read it, we also at the same time in memory we're going to maintain metadata about all the clusters that we've created thus far. Right? We're going to bring a chunk of the data into memory. We're going to update the metadata about the clusters, and then we're going to throw that chunk of data away. And then we're going to bring the next chunk of data into memory. And we're going to continue with this process until we've gone through all the chunks of data, at which point we've ended up with our final clustering. Okay? This is the high-level overview of the BFR algorithm. So to summarize, the points are read from disk, one main memory full at a time, right? And most points from previous memory loads are actually summarized by simple statistics. Since you don't have space to store all those points, we summarize all those points with simple statistics, and we'll see what these statistics are going forward. To begin with, we're going to, when we load the first set of data or the first chunk of data into memory, we're going to select the initial k centroids for the k-means algorithm from that chunk of data using some sensible approach. For example, we might use one of the techniques that we saw in the k-means lecture prior to this. Now, as we go through, we'll see that points fall into three different categories that we need to keep track of. The first category of points is called the discard set. And the discard set of points are points that are close enough to the centroid of an existing cluster. So if a point is close to the centroid of an existing cluster, then we just update the metadata or the statistics of that cluster to account for the fact that we've added the new point to the cluster, and then we throw the point away. That's why this set of points is called the discard set, because we discard points that are close enough to the centroid of a cluster. So we don't need to keep them around any longer. The second set of points is called the compression set, or the CS. Now, these are points that are close to each other but are not close to any existing centroid, right? So these points form a separate mini cluster of their own, but they don't really naturally merge with any of our existing K clusters. So what we do with these points is that we compress them into mini clusters and summarize them, but we don't assign them to any of the existing clusters. And the resulting summarized sets are what we call the compression set, or the CS, and we'll see more about this later. Finally, we have the third set, which is called the retained set. And the retained set contains points that are kind of isolated. They don't fit into any of the existing clusters, and they're not close together to any of the other points, so they can't be made part of any compressed set. They're kind of outliers that are on their own, and these are called the retained set, or RS. These are isolated points, and we might eventually, in the future, as we load in more points, we might find that they get close to a compression set, but at the moment they are too far away to be assigned to, and they just kept isolated as part of the retained set of points. So the retained set of points is the only set of points that we actually have to keep track of in memory. Both the discard set and the compression set, we can throw away the actual points and only keep metadata about the points in memory. So here's a picture that will help you visualize these three classes of points. Remember, there are three sets that we need to keep track of: the discard set, the compression set, and the retained set. So here's a cluster, one of the K clusters that we're maintaining, and here's its centroid. And any point that's close enough to the centroid of this cluster is assigned to this cluster and becomes part of the discard set. We don't need to keep track of the point anymore. Now here are a bunch of smaller mini clusters. Now these are compressed sets. These the points in these mini clusters are close to each other, so we could actually cluster them into these mini clusters. But they're too far away from any of the existing clusters, so I can't really merge the points in this mini cluster with this cluster here. But I can keep track of them independently as a mini cluster. So the points that are in these mini clusters are said to be in the compressed set. So for these points, we just need to keep track of the mini cluster. We don't need to keep track of each individual point. And so these points are in the compressed set. And finally, we have isolated points that are not close to any mini cluster, they're not close to each other, they're not close to any of the existing cluster. So we just keep track of them independently as individual points, and these are the points that are in the retained set, or RS. So let's look at how we summarize this sets of points that are in the discard set. Remember, the discard set, a particular discard set pertains to one of the k clusters that we're keeping track of. So for each of the k clusters, we keep track of the number of points in the cluster. Let's call that n. We keep track of a vector sum, and sum is just the sum of the points that are in the cluster. So there are n points in the cluster, and we sum them dimension-wise, and the sum vector is just the sum of all the points that are in the cluster. So the ith component of the sum vector is the sum of the coordinates of the points along the ith dimension, and so on. And similarly, the sum square vector is just the sum of the squares of the coordinates. So the ith component of the sum square vector is the sum of the squares of the coordinates of all the n points along the ith dimension. In a moment, it will be apparent why we maintain the sum and the sum square vectors. It should be fairly apparent that we need to keep track of the number of points in a cluster. Notice that if d is the number of dimensions, we can represent a cluster by 2d plus 1 values independent of the size of the cluster. The cluster can have 10 points or 10 million points. The number of values that we use to represent that cluster is 2d plus 1, where d is the number of dimensions. Why is this? Well, we need one point or one value to store n, the number of the number of points in the cluster. The sum is a d-dimensional vector, and the sum square is another d-dimensional vector. So overall, we need 2d plus 1 values to represent the cluster. And this is independent of the number of points in the cluster. Now, the centroid of the cluster is just the average along each dimension. And it's very simple to calculate the centroid. We just have to go to the sum vector and divide each component of the sum vector by n, the total number of points. And then we end up with a vector that's just the centroid of the cluster. We can also calculate the variance of the cluster along any dimension. The variance of the cluster along the ith dimension is just given by this formula here. You take the sum square values along the ith dimension, divide them by n, and then subtract the square of the sum values along the ith dimension divided by n. This is from elementary statistics, the formula for the variance from elementary statistics. And the standard deviation along the dimension I is just the square root of the variance along the dimension I. Right? So you just take the variance along dimension I, and you take the square root of that, and you get the standard deviation along dimension I. So now it should be apparent why we maintain the sum and the sum square of vectors for each cluster, because using them and the number of values in the cluster, it's quite easy to compute both the centroid of the cluster and the standard deviation along every dimension. Next, we're going to look at how we actually do the clustering. Remember, we're going to page in one chunk of data points at a time, and we're going to update the cluster metadata. And we just saw the metadata that we keep track of for each cluster, the n, the sum, and the sum square values. So once we have a chunk of points in memory, we're going to find the points that are sufficiently close to a cluster centroid. And we'll see what sufficiently close means in a moment, but let's just assume that for now, we know that given a point, that it's sufficiently close to a cluster centroid for one of the k clusters, which means that that point is in the discard set. We're going to merge that point in the cluster and throw the point away. And here's how we do that. We add that point to the cluster, and when we add the point to the cluster, we have to update the n, the sum, and the sum square for that cluster. To adjust n, we just have to increment it by 1 to indicate that we've added a value to added a point to the cluster. To increment sum, we just have to add that point to the sum value for the cluster. And to update sum square, we just have to compute the square of the values of that point along each dimension and add that to the sum square vector for the cluster. Now we see the advantage of the n, sum, and sum square representation. It's very easy to incrementally add points to a cluster and increment the statistics for a cluster without doing complex computations. Now the points that are actually close to the centroid of a cluster, we've added to a cluster. However, the points that are not close to any cluster, we know how to deal with those points. What we're going to do is to take these points, the points that are in this memory load of points, but that are not, that we've not added to the discard set, and we're going to take those points and we're going to add in the old retained set, those points from before that we've not done anything with. And we're going to take these new points in the old retained set, and we're going to use some main memory clustering algorithm to cluster them all. You could use either k-means clustering, or we could use hierarchical clustering, it doesn't matter. We use any main memory clustering algorithm and we cluster these points. Now once we do that clustering, the clusters that come out, which we'll call these the mini clusters, they go into the compressed set. And the outlying points that don't fall into any cluster in this, according to this main memory algorithm, go into the new retained set. Now we've added a whole bunch of mini clusters into the compressed set. And it might happen that two of the new mini clusters, one of the new mini clusters that we're adding to the compressed set is actually very close to one of the existing mini clusters, so we might want to merge these mini clusters in the compressed set. So that's, we will see in a moment what metric we might use to determine that mini clusters are close enough and need to be merged. Right? So we might consider doing that. And if this is the last round, if this is not the last round, we just stop at this point and we just read in the next chunk of data points into memory. But if this is the last round, then we take each mini cluster or each compressed set in the CS and we merge it to its closest cluster centroid. And we take each point in the retained set or the RS and we assign it to its nearest centroid. And that's the end of our clustering. If this is not the last round, we just keep the compressed set and the retained set as it is, and we read in the next chunk of data points, and we repeat the whole process again. So at the end of the algorithm, we've gone through the entire data set exactly once. We paged the entire data set to memory exactly once, and we've produced k clusters. Now, there are two questions that we left unanswered during our discussion of the algorithm. The first question is, how do we decide if a point is close enough to a cluster that we will add that point to that cluster? We hand-waved a little bit about this during our discussion of the algorithm, and now we're going to look at a way to determine if a point is close enough to a cluster that we will add it to the cluster and make it part of the discard set. The second question, which we left unanswered, is how do we decide whether two mini clusters in the compressed set are close enough that they deserve to be combined into one mini cluster, or whether we should just leave them as separate mini clusters. Let's look at that next. Let's start with the first question, which is, how do we decide whether a point that we've newly read in is close enough to one of the cluster centroids that we decide to add that point to that cluster? The key concept here is something called the Mahalanobis distance. And the Mahalanobis distance quantifies the likelihood of a point belonging to a centroid. And the Mahalanobis distance depends very crucially on our assumption about the points being normally distributed about the centroid along each dimension. Let's say cluster C has centroids C1 through CD. Remember, there are D dimensions, and the value C1 through CD represent the mean along each of the D dimensions. So the centroid of the cluster is C1 through CD. And let's say the standard dimensions along those dimensions, standard deviations along those dimensions are sigma 1 through sigma d. Right? And let's say we have a point x1 through xd. Now what we need to determine is if this point P is close enough to the cluster C so that we can add the point P to the cluster C, or is it too far away to be considered part of the cluster C. We're going to define the normalized distance of a point along dimension I from the centroid to be yi, which is xi minus ci divided by sigma I. We take the value of the point along the dimension, subtract the centroid along the dimension, and divide by the standard deviation along that dimension. And this gives the normalized distance along that dimension. Now consider a point along dimension I that is at a distance of 1 standard deviation away from the centroid. What this means is that xi minus ci is equal to sigma I. But if xi minus ci is equal to sigma I, then the normalized distance in dimension I, which is yi, is equal to 1. So yi measures the number of standard deviations away from the mean along dimension I. The Mahalanobis distance of point P from cluster C is the square root of the sum of the squares of the normalized distances yi along each dimension. Let's see how we use the Mahalanobis distance. Now suppose point P is 1 standard deviation away from the centroid along each dimension. Now we saw that in that case, each yi is going to be 1, since yi measures the number of standard deviations away from the centroid along dimension I. And since there are d dimensions, the Mahalanobis distance of the point P from cluster C is going to be square root of d, where d is the number of dimensions. Now going back to our bell curve from the Gaussian or normal distribution, the probability that each yi is equal to 1, or that a point is 1 standard deviation away along each dimension, 1 standard deviation or less away in each dimension is 0.68. It's 0.34 plus 0.34 here. And so the probability that a point is at a Mahalanobis distance of square root of d or less is 68%, or 0.68. of those points are in this area for each dimension, right? And similarly, the probability that the Mahalanobis distance of a point belonging to a cluster is within 2 times square root of d is 95%, and 99% of points have Mahalanobis distance less than 3 times square root of d. So this sort of motivates us to formulate the Mahalanobis acceptance criterion for the BFR algorithm, which is to accept point P into the cluster C if its Mahalanobis distance from the cluster centroid is less than some preset threshold. For example, we might pick the threshold to be 3 times square root of d, which means that there's less than 1% probability that the point does not belong to that cluster. The second question that we left open during our discussion of the algorithm was whether 2 subclusters or mini clusters in the compressed set should be combined or compressed into each other. The simple way to address this question is to compute the variance of the combined subcluster. The way we do that is to just add the n, sum, and sum square values of the 2 clusters to each other. And then we can compute the centroid and the variance of a hypothetical combined subcluster. If we find that the combined variance is below some threshold, then that might indicate to us that these 2 clusters actually do belong together, and we might decide to combine those 2 subclusters in the compressed set into a single cluster. Now, this is just one approach to answer this question, and there could be other approaches. For example, some dimensions may be more important than others. In the data, for example, height may be more important than weight. and so we might want to weight the dimensions differently. Or we might want to use a density-based metric like we studied when we looked at agglomerative clustering.